Hey everybody, welcome back to Young Engineers of Today, Amazing Mechatronics. So we're going to continue with Arduino. This time we're going to work with the potentiometer. Now this one's going to go fairly quickly, just because we're going to be, there's less, it's less important in and of itself. However, it does set the stage for future things, future lessons involving servos and things like that. And plus, it's good to understand how a potentiometer works. However, on the other hand, it is analog input through and through. So it's not like we're going to be covering any groundbreaking topics necessarily with this, other than how a potentiometer works, which is just in general a useful thing to know. Potentiometers, though. Potentiometers are variable resistors. All that means is it's just a resistor that you can adjust. In the past, when we've wanted to work with resistors of different values, you've had to unplug that resistor and plug in a different resistor of a different resistance value, which is pretty unwieldy, especially if you want the resistance of a circuit to change while that circuit is running. You can't exactly just pull out a resistor and then replace it with another one. Imagine if every time you had to change the volume on like your computer speakers, you had to pull a resistor out of the back and plug in a new one. That would be pretty annoying. So potentiometers are a way around that. We can instead get a nice handy volume knob or set of buttons or something like that on our computer speakers or our home stereo or whatever in order to adjust the volume. That is a potentiometer. You can use those to control the brightness of an LED. You can control a servo, a bunch of different stuff. And we can actually take a look at controlling a servo with a potentiometer. It's kind of neat, I think. So a potentiometer contains a resistive element inside with two stationary terminals. This is how it works. And it also has a wiper, in quotes, because that's kind of like it's kind of a term for it that's sort of a colloquial term, but at the same time, it's kind of become the accepted nomenclature for it. So wipers in quotes. But anyway, it has a wiper that can move in a clockwise fashion along the resistive element. So as you can see, since the wiper conducts electricity, you might have your circuit hooked up and there could be like an LED here, right? Boop. Look at that LED lighting up. Pew. And then you've got, a battery hooked up to A, and then, this is all hooked up to the ground. So in our little example here, you got electricity traveling down this thing, and it travels around the resistive material back into the battery. So there is a high amount of resistance if you go all the way across this. Now, when you spin the potentiometer, this wiper moves to the left or the right. So the wiper could be pointed over here, it could be pointed down here, it could be pointed over here. But the important thing is the wiper is conductive. So electricity can travel across it. So it hits here, and it travels across it and down this way, and into our LED and blah, 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 blah. I've really screwed this up by making the electricity jagged lines. This really would be so much easier to look at otherwise. But anyway, regardless, the electricity will have to travel at least some length of resistive material, which becomes a built-in resistor for anything hooked up to the middle. As you turn the wiper this way, it has to travel across more resistive material in order to get to the wiper and travel down this middle terminal, which means that the resistance of this circuit increases. As you turn the wiper this way, it has to travel less of the resistive material, thus reducing the resistance of the circuit on the central terminal. If you turn it all the way to the end over here, like if it gets to the point where it can touch, B, well then the electricity will be evenly split between the two, and you'll probably get less resistance along B, depending upon how your circuit's set up. You may not. You may, but you may not. In which case, you may get very little electricity traveling down the central terminal, effectively turning off the circuit. So it's a very simple property, or a very simple concept. Basically, just you can imagine, let's see here. I'm trying to think of a good analog. Well, it's essentially just by changing the physical distance the electricity has to travel across the resistive material, you change the resistance on that middle circuit. Just this middle one right here. A and B will always be the same, no matter what, but the middle circuit will change based on where you have this rotated to. It can move in a clockwise fashion along the resistive element. Now, obviously, it can also move counterclockwise. It can move both clockwise and counterclockwise. It's not restricted to just clockwise. Otherwise, you would have a one-use potentiometer. If you could imagine that you could only turn the volume down on a stereo and never up. It just the knob doesn't turn back, so you got to turn it to like a comfortable volume, and then only listen to it when you need it to be that loud, because if you ever need to listen to it and it needs to be quieter, then you're going to turn it down, but it's never going to be loud again. Yeah, that wouldn't be ideal. So anyway, that's how a potentiometer works. Now let's go ahead and just build a really simple circuit that takes advantage of this potentiometer. And all this is going to do is it's going to take in an analog value and turn on the LED. Well, we don't even need the LED to turn on. Is this thing gonna? Okay. Okay. So they are gonna take advantage of it. So I'm gonna go ahead and open up circuits.io, just like before. Boop. And just like before, I'm gonna go and create a new electronics lab. And we're going to be looking at our good old breadboard, just like we have a million times before. Let me go ahead and drag it over here. Boop. Components, bring in an LED and a regular resistor, just like we always do. Bring in an Arduino Uno R3, just like before. Like you're sensing a trend here. And then I can just type in potentiometer or potent, and potentiometer pops up. So now we got the three components that we're going to be using for our circuit. We have our LED, we have a resistor, we have a potentiometer, and then we have our Arduino on our breadboard. I'm going to rotate the Arduino. Should all be pretty familiar stuff to you guys. And let's go ahead and build our circuit. So we're going to want a resistor to be 330 ohms, just like we have for basically every time we've hooked up a resistor LED combination, right? It's always been a 330 ohm resistor. And that's just so that it lines up with the SparkFun kit. You know, strictly speaking, it doesn't have to be 330 ohms. If we made it weaker, the LED would be brighter. If we made it stronger, the LED would be dimmer. But obviously, we don't want to make it too weak because the LED might then pop, and we don't want to make it too strong because then the LED might not light up at all. So we want to be sure that it's within a sweet spot, and a lot of times the only way we really know that is by referencing the LED, seeing how many watts it can take as a maximum and that kind of stuff. But that's just an aside. Let's go ahead and build a circuit. So we got the anode and we got the cathode. Let me go ahead and hook that up. We'll hook the resistor up to the ground rail again. So it's hooked up to the cathode to the ground rail like it always is. The LED is going to be hooked up to, let's say pin, we'll do pin 13. So in case our LED circuit is hooked up all wonky, we can at least see pin 13 lighting up in order to give us an idea of whether or not it's operating properly. And I'm going to hook up the ground rail to the ground on the LED, like so. Bam, black, done. And I'm going to hook up the 5-volt to the power rail so that we have that. Red for power. Boom, bam. Now, we're going to hook up the potentiometer. So obviously we're going to have to rotate the potentiometer, right? Because we got 3 separate terminals and they have to be hooked up to 3 separate rails. As we all know, we can't have it hooked up to the same rail because then otherwise we get a wicked short circuit and it's, you know, bad times. What have I done? Did not mean to grab that. There we go. So I'm going to rotate it to the side. So bam, we got 3 separate terminals hooked up. Now, we're going to pull in power onto the first terminal, the top terminal. And I'm going to sneeze. Oh, excuse me. So we're going to pull in power to the top terminal on the potentiometer. And we're going to pull out ground on the bottom terminal. So remember the diagram, A and B are unaffected. So we're going to have a complete circuit running through A and B already anyway. However, as we spin the potentiometer and change the position of the wiper, that's going to affect the output onto W. That's what we're interested in. So we're going to have an output from W go into analog 0. Let me go ahead and get rid of that one and align this stuff. And let's make it purple. So no, let's make it pink. So not really. Let's make it brown. Not particularly. This is just a difficult breadboard wire to see. We'll make it white. Now that's even worse. Turquoise. Nope. Good Lord. Okay, we'll go back to pink. Okay, so it might be a little bit difficult to tell from the red, but whatever. We've got a input running from the middle terminal. Again, remember the diagram here. Running from the middle terminal on the potentiometer across the wire down into A0. So our input in this case is going to be A0 on the Arduino. And then that's going to be reading values in, and it will send a value out to pin 13 based on that. Now, what do you notice about pin 13 that might be missing? We're doing something a little bit different from analog input last time around. I'll give you a hint. It's missing that, right? That little tilde right there. So what does that mean? Well, what does it say down here that means on the Arduino itself? It is, yeah. Well, actually, since it's missing that, it's not a PWM pin. But excellent, yeah. I like that you picked up on that. So it is not a PWM pin. So this is just a straight up digital pin. It can only send on or off. Well, I mean, PWM pins can only send on or off as well, right? But what's special about PWM? Or pulse width modulation? Well, pulse width modulation can basically turn off and on really fast in order to simulate an analog circuit, right? Or an analog output. So in this case, it cannot. It can only be just a regular digital output. So we can only send on or off. We cannot send on or off in a specific sequence to make it look like an analog circuit. With that done, though, that's our circuit. So let me go ahead and open up the Arduino software. It's starting up in the background. Well, yeah, in essence. Exactly. With a PWM, yeah, you would be able to do that and thus affect the average or apparent power coming out, or voltage, apparent voltage coming out. So this means that we're going to be doing something a little bit different from the analog input, as I already said. Set up the void setup and void loop that you always need, always and forever. And then we'll do our general pin mode setups, just like we've done for pretty much every single Arduino program. So we're going to set pin 13 to be output, and we're going to set pin A0 to be inputs. And that is a numeral 0, that is not an O. I'll put an O right next to it so you can compare the two. But yeah, so that's A0. So now we got pin 13 set to output and pin A0 set to input. Just like we got here, A0 is input, 13 is output. Should be stuff that you guys are all pretty familiar with at this point. So, where do we go from here? Well, we're actually going to set up a threshold. We could do that. Let's do this, though. I like this one better. So what we're going to do is we're going to create a variable called sensor value, and it is going to hold the value from A0. So sensor value is going to hold whatever analog A0 returns. In this case, it's going to be basically the power sent in from the potentiometer. Then we're going to turn the LED on. Then we're going to turn the LED off. Good Lord, I cannot type today. Wow, fingers all over the place. So here's the thing. We're going to turn the LED on, we're going to turn the LED off. But the catch is the delay is actually going to change from cycle to cycle, presumably. The delay, instead of being a fixed number like 1,000 or 100 or 25 or 985,632 or whatever, what we're going to do is we're going to set it to be sensor value. So now the delay is going to be whatever sensor value is. That is to say, whatever the power reading is coming in from the potentiometer. So as we decrease the potentiometer's resistance, the LED is going to wait longer in between each blink. As we increase the resistance on the potentiometer, the value into A0 is going to get smaller, and thus the LED will blink faster. It's a little bit backwards from, maybe what you were expecting, but we can actually very easily see this in effect on this circuit. So let me go ahead and open up the code editor. And just so you guys can compare what you have, there's the code. I don't want to leave you guys, high and dry and without being able to look at the code. But by the same token, potentiometer is pretty fast, so I want to get through it pretty quickly as well. So let me go ahead and upload the code. As you can see, the LED is blinking at a reasonable pace. As I turn the potentiometer up, well, this is a bit backwards from what's expected. No, it's not at all. As I turn the potentiometer up, the LED blinks faster, faster and faster and faster. Eventually I get to a point where the LED is blinking so fast that the program essentially can't simulate it, so it just kind of looks dim. We can also see it blinking over here on the pin 13 debug LED. See how fast we make it go. That's about as fast as we can make it go. And then we can turn it all the way back down and it slows down considerably. Now again, if we were to do a serial print on whatever the value is in A0, or by extension sensor value, or sensor value by extension A0, we will see it increase as we turn down the potentiometer, because again, we're reducing the resistance here, so there's a larger electrical signal being sent into A0, thus delay is becoming larger. We turn it up, the resistance becomes larger, there's less power going into A0, thus the number becomes smaller, so the delay becomes smaller and the LED blinks faster. Pretty self-explanatory stuff, right? And it took us, I don't know, maybe 10 minutes to make. Raise your hand if this makes sense to you. All right, raise your hand if there's something that's still not quite like clicking with you. Well, if you got any questions about anything, throw them in the question box. See if we can't tackle those as well, because I assure you, you are not the only person in the world who has this question. And in fact, somebody in this class might have it as well. But if you think you got a handle on it too, that's cool too. I mean, I'm not trying to put anybody on the spot. I'm just saying. I encourage you guys to ask questions you might have, just because you never know what the answer might be. You might assume it's one thing, but it might actually be something different. All right, well, congratulations. This all made sense, which is, on the one hand, I'm sure pretty basic, but on the other hand, how long did it take us to do this? Not very long at all, right? So from that perspective, you guys are really getting a lot more comfortable with the Arduino. So that's a good sign, right? It's always a good sign. So we got that working. Cool. Let's go ahead and let's move on to the next lesson. Just like right now, let's not waste any time, because I believe It might be servos, in which case we're going to be spending a decent amount of time with that. So let's see here. Indeed, they are servos. Hopefully we can get through servos and we can spend some time with transistors as well, because that should be pretty cool. Transistors are pretty awesome. Transistors are how your computer works. So from that perspective, I'm pretty okay with transistors. But they're a way of sort of intelligently distributing electricity, in a sense. They're simple, but they can be used for a lot of different logical circuits and things like that, which is pretty impressive. So anyway, servos. That's what this lesson is going to center around. And we're actually going to take advantage of the potentiometer in order to modify it. So basically, this is just going to be what is a servo, and we're going to make the circuit, and we're going to code the servo. We're going to code the Arduino software so that the servo will run. Who knows how far we'll be able to get into the lesson today. I imagine at the very least we'll be able to complete the circuit construction and at least get started on the coding, but I don't know for sure whether or not I can guarantee that we'll be able to finish the coding today. But we'll see. So what are servos exactly? Well, servo motors take a timed pulse and convert that pulse into motion control. Most have integrated gears and a shaft that can be controlled precisely. So that's kind of all vague. Servos are a type of motor, but they operate differently from regular motors. Regular motors, you can think of like, I don't know, like on an RC car or on a, let's see, what else is there? Like little remote controlled vehicles, like cars, helicopters, quadcopters, and stuff like that. They use motors. Electric cars have motors because they convert electrical energy into forward motion and so on and so forth. That's not all that defines a motor, but anyway. When you think of a motor, you think of something that just spins a shaft over and over and over and over and over and over and over again. The more powerful the motor, the faster, or with increased torque, can it spin that shaft? That was an awkward way to put it, but either way. Motors, generally when you think about them, it's how fast can you spin the shaft, or how powerfully can you do it? Servos work a little bit differently in the sense that most servos, unless they're very expensive servos, don't actually spin 360 degrees. And certainly they can't really spin continuously. Again, unless either they're A, very expensive, or B, very imprecise. The reason why I say imprecise is because servos have a different function. Servos, well, like it says here, take a timed pulse, so maybe it'll send an electrical pulse every, I don't know, 90 milliseconds or something like that. Faster than that, but it could do that, or like 15 milliseconds. And the servo will take it as a signal. It'll say, all right, I'm receiving a timed pulse every 15 milliseconds. I am going to turn 75 degrees and stop. Or I'm receiving a timed pulse every 90 milliseconds. I'm going to turn 10 degrees and then stop. So it's got a 0 point that it starts out at and will always return to. Imagine this being like the arm of the servo. Okay. Imagine this being like the arm of the servo. And it's got like a zero degree point that it starts at. And it will receive a timed pulse and it will turn a specific amount. So, before long, it'll be pointing here at 75 degrees. Then it'll stop receiving the pulse, and it will return to 0 degrees again. So in doing this, you can control exactly how a servo is positioned. So whereas a motor would be good for a vehicle, a servo would be good for the arm on a miniature dump truck. Terrible example, but you could. Or like arms on, a robot, fingers on a prosthetic hand. You could use servos for stuff like that. What else? Readouts on a digital counter with an analog display. So like, you think about like the speedometer on your car or something like that. It might take in the information digitally, that is, a computer reads it and stores the values like, oh, you're going 60 miles an hour. And then it can translate that into a timed pulse to send to a servo so that the servo turns the little speedometer needle to 60 so that you know you're going 60 miles an hour. That kind of thing. So yeah, the servo motor internals allow for the servo shaft to be positioned at an angle, usually between 0 to 180 degrees. That's going to be a lot of servos. The wider the the turning ability of the servo, so like if you can do like a full 360 degrees or even continue after that, the higher the potential for the servo to be inaccurate. That is to say, it will not point at exactly 100 degrees when you mean it to. And a lot of that just has to do with the fact that as you increase the number of degrees that a servo can turn, it has to either be able to accept larger and larger sets of timed pulses, or those sets of timed pulses have to apply to less granular values. So let's say, a 15 millisecond pulse on a servo that can turn 0 to 180 degrees means turn 10 degrees. If the servo only turns 15 degrees, well, we can be more specific with it because we can still send it a 15 millisecond pulse, right? It can mean 10 degrees, but we can also make it mean 10.00 specifically. And if it receives a 16 millisecond pulse, it can turn 10.10 degrees. So you have that sort of fine motor control over it. If it's 0 to 360 degrees, 15 millisecond pulse could mean 10 degrees. A 16 millisecond pulse could mean 13 degrees, and there's no in between, that kind of thing. Or it might be that a 10 millisecond pulse is 9 degrees because they can't work out the math so that it's 10 degrees, whatever. But yeah, so the servo motor is controlled by a timed pulse sent by the code, which tells it when to turn. So it's, and by how much. That's really the more important thing. When to turn is very important too, but by how much is yeah. Or I guess when to turn and when to stop turning. That'd be another way of looking at it. But anyway, so hopefully that makes sense. As servos get a wider range of motion, they become less accurate just by virtue of the fact that it's going to be harder to be able to control where they stop. Unless, of course, you're talking about very expensive and potentially very slow servos as well, in which case they tend to be very accurate. And they work differently from regular motors in the sense that they orient themselves in a specific direction as opposed to just turning and turning and turning and turning and turning. So the servo shaft is, again, controlled by a timed pulse, which dictates how fast it rotates. 0 degrees, 900 microseconds. 90 degrees, 1500 microseconds. 180 degrees, 2100 microseconds. Not necessary to know for the main lesson project, but for those who like challenging prompts, keep this information in mind. And that might be something like, how would you manually send a timed pulse to the servo motor to turn it to where you want it to turn, things like that. So this circuit is going to be, it looks pretty complex, but it's actually not too bad. We're just hooking up a single servo to the Arduino. So it requires a few things in order to get running, but all in all, it's not too bad. So here's the important thing to note. A servo generally has 3 wires running off of it. You've got a red wire, you've got a black wire, and you've got a white wire. So the red wire is going to be power, just straight up power to the servo. That's how it gets enough power in order to be able to turn. The black wire is going to be ground. That completes the circuit on the servo so that it has the ability to turn. So it has two wires dedicated just to providing enough power so that it can turn whenever it needs to. Then the third wire is a signal wire. That's the white wire. The white wire is the wire that receives the timed pulse to tell the servo when and by how much to turn. So you've got power, you've got ground, and you've got signal. As we could see in this diagram here, V plus, power, ground, ground, sig for signal. So let's go ahead and hook this up. So I've got a new circuit already set up. Bam, pull that out. Go into the components tray. We're going to not need an LED or a resistor for once, for the first time ever. We're going to pull out an Arduino. We're going to pull out a servo. And you might have to scroll around a little bit in order to find it. Going to pull out a micro servo, not just a regular servo, but a micro servo. And for later, for ha-has, we're going to pull out a potentiometer. So there, now we've got a servo, we've got an Arduino, and we've got a potentiometer. Let's rotate the Arduino like we always do. Let's bring the servo down here. So now, you might notice that this servo, when you have it highlighted, they're all blue wires, but if you click away from it, look at that. You got a red wire, you got a red wire, you got a white wire, and you got a black wire. If we mouse over these, power, signal, and ground. So they went through a fair amount of work in order to ensure that this followed like a similar sort of aesthetic from working with just regular electronics. So that it was as easy and painless a transition as possible to like physical electronics. So we're going to hook up the power to the power. Ground to the ground. Like so. And we're going to hook up pin 9 to the signal on the servo. I'll make it white so that let's just do this. Oh, that's not really going to work. Oh well. Whatever. We're going to hook up power to the power on the servo and ground to the ground on the servo. And if you're in a situation, where like you're not, like you hooked it directly up from power on the Arduino to the servo and ground from the Arduino to the servo, that's totally fine too. Like it's not the end of the world. I'm just doing that so that we get into the habit of hooking up the power and the ground rail. because a lot of your circuits are going to be utilizing those, as we've said before. Not necessarily these circuits, but circuits in the future. So anyway, we've got power on the servo hooked up to the 5-volt on the Arduino. We've got ground hooked up to the ground on the Arduino, and we've got the signal hooked up to pin 9 on the Arduino. So now we can actually get started on the coding aspect. Notice how I'm not even worrying about the potentiometer for now. First, we're just going to get the servo to move on its own, and then we can try and control the servo with the potentiometer. So now let's open up a new one. And by open up, I mean just delete all the old code. Bam, done. So servos on the coding side also introduce a new concept to programming. And it's not something that's, what am I trying to say here? It's not something you guys necessarily haven't dealt with before, and it's not something that, strictly speaking, is going to be, something you're going to be dealing with all the time, although as you get further into programming, you will probably get very familiar with these things, and these things are called libraries. Because here's the thing, depending upon the programming language, you might have, the programming language might have no idea how to do anything. For example, C, in its base language, like in its base version of the language, does not know how to write to a monitor. Just like output stuff on the terminal, it has no idea how to do that. There is no built-in base command in C in order to print something out onto a monitor. And that's because, I mean, C is meant to be a very lightweight, low-level language, and it can be used in stuff like airplane black boxes and things like that, where it's not necessarily going to be talking to a terminal the entire time and stuff like that. But regardless, that information doesn't exist. But yet, a lot of programs are written in C. Not as much nowadays as there used to be, but on the professional side of things, there are a lot of programs that are written in C. A lot of programs that are maintained in C. If you're ever learning C, you'll have to write things to the terminal so that you can tell exactly what's going on, print something to the screen, and take input from the user, neither of which are things that C knows how to do intrinsically, without getting into the whole thing about, whatever. Anyway, so you've got a couple of options, basically. You can either, every time you write a new program in C that needs to write something to the monitor or take input from a user, you need to rewrite all of that code that does that for you. Basically tells it what a monitor is and tells it all the, the Unicode and ASCII codes for letters, tells it how to print a letter to the screen and what order everything should be printed in, tells it how to allocate memory for something to be printed to the screen, tells it how to translate it into something that can, that the monitor can understand, and blah, 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 blah. Like a lot of work. Or you can utilize something called a library, and a library is basically just a collection of code. It's literally just some number of files of code that somebody else has spent the time to make and made it inclusive, so you can use it too if you want to. Because there's no sense in reinventing the wheel every time a new program needs to be written, right? There's no sense in rewriting how to write to a monitor every time you want to use C. If you were somebody who did that on a regular basis, you'd probably just save a template that told the computer how to write to the screen, right? And then you would build off of that with whatever code you needed. Well, that's essentially what a library is. It is a template set of code that includes all of the instructions that you need for whatever you're trying to do, and allows you to just easily include it in your code so that you can do whatever you're looking to do and utilize those, basically those special features. And a lot of programmers use libraries. Libraries are big. Libraries are very important because libraries are one of the best ways to expand functionality of a code, and they sort of get, you know, passed around. Sometimes you have to pay for libraries. Sometimes most of the time libraries are distributed for free. But there are libraries for everything. There are libraries for memory management. There are libraries for making pretty colors on the screen. There are libraries for, you know, interfacing with a database. There are libraries for whatever. In this case, we're going to utilize a library that already knows how to make an Arduino communicate with a servo. I almost said a server, and that would be a very different thing. So that's what we're going to do, is we're going to utilize this library so that we can have the Arduino talk to the servo and turn it like in the ways that we want it to. So all of that buildup for one command, a pound sign or a hashtag or whatever, pound include, and then in angled brackets, servo with a capital S dot H. And what that is it's called a preprocessor directive. Essentially, it's just something that the computer handles before it starts compiling the code. And it says, hey, what we want to do is we want to include all of that information in that one file about servos. And that's all of that code. It's going to be how to interface with the servo, how to translate what we want into something that, you know, is a timed pulse that's useful for the servo, how to get a servo to start communicating with an Arduino, all this kind of stuff, what a servo is, blah, 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 blah. So by doing that, we are just basically kind of like, let's see here. We're just attaching a bit of functionality to our code. It's like snapping on a special lens to a cell phone so it can do microscopic pictures. Sort of, kind of, almost, kind of, sort of. In essence, just attaching something so that it has increased functionality. So we're attaching the servo information so it can do that. Now, this means that we have some additional sort of code that crops up as a result of this. There's some more stuff that we're going to have to sort of work with. One of those is declaring the servo so that it basically the code is aware of it. Unfortunately, I'm a little bit scatterbrained right now, so I can't really think of a good analogy for this, so I'm just going to go ahead and say it. It might make sense, it may not. If it doesn't, don't sweat it. What we're essentially doing here is we're creating an object that models the servo inside the code. It's going to act as our proxy in the code. And we make changes to this modeled servo in the code, and it will make changes to the servo in real life. In essence, it's not quite as one-to-one translation as that, but it is, in essence, what we're doing here. So we've got my servo, which is an object that resembles our servo in the code. And we declare it with a capital S servo. So it's capital S servo space my servo. You can name this whatever you want. You can call it, well, I always say Tom Servo, not because of my name, but because of Mystery Science Theater 3000. Or we could call it, you know, Nimbly Bimbly, or we could call it Ukulele Storm 2016, whatever. You can name it whatever you want to. It's probably a good idea to give it a useful name, though. But this is just like a variable. We're storing this information about the servo in something that that's has a name that's useful to us so that we can reference it later. So now that we've created this my servo object, let's go ahead and attach it to pin 9. And all that's doing is simply setting it up so that the Arduino is aware that there is a servo attached to pin 9. And again, no surprise there, pin 9. Now it's specifically pin 9 because that's the signal circuit. That's the one that the Arduino is interested in. It's always sending out power on the 5-volt and it's always receiving power on the ground. However, pin 9 is going to be the interesting pin here because that's the one that's actually going to control how the servo spins. So by attaching it to pin 9, we're telling the Arduino, hey, there is a servo that has the signal wire hooked up to pin 9 on the Arduino. We are not going to have enough time to finish this. So why don't I go ahead and do the poll questions now. We'll pick this up on Thursday where we left off. We'll get through it, spend some time on transistors as well. Hopefully, I might have some sample questions from Mr. Dubik that I can give to you guys so that you at least have an idea of what you're looking forward to. But yeah, let's go ahead and call it a class now. We'll do the poll questions. We'll meet up on Thursday, and that should be our, I believe, last class. So we're getting close to the end there.